Hi class, welcome to another session on digital principles in system design. Today we are going to see what is parity generator or parity checker. So what is parity? To be very, that's the first question that comes into the mind, right? So parity refers to the number of ones in a binary digit and it can either be even or odd because, the number of ones in a binary digit can either be even numbers or odd numbers. It is mostly used to detect errors in a transmitted signal. Now, what does that mean? You have two circuitries. One is transmitting a signal and the other is receiving. Now, the mode of transmission and reception can either be UART, can be SPI, can be wireless, anything. So, what is the assurance that whatever message I'm transferring is actually the message that is getting received? Because if there is an error, then every other function that is dependent on this message that has been sent is going to get affected. So we have to be absolutely sure that whatever we are transmitting is getting received properly, and that's why we use these kind of error detection or methods. Now you can use checksums if you want to, and you can use a start bit and an end bit. So it is up to the discretion of a designer. But parity is also one of the options to have that is used to detect errors. Often, the most significant bit of a binary word is used as the parity bit, and it is either set to 0 or 1, such that the parity of the whole word is either even or odd. Now, exclusive OR gate, we know the truth table of exclusive OR gate. It gives an output 1 when either of the inputs are 1, right? If both inputs are 0 or both inputs are 1, then the output is 0 of an exclusive OR gate. So this is the perfect gate for us to detect an error. So a parity checker actually generates an error code or flags an error when it detects an even parity signal from an odd parity generator and vice versa. So if the device is programmed such that we know that the transmitted signal is going to be of odd parity, so when the received signal undergoes parity check, and if it has even parity, then the parity checker would flag an error saying that the data is improper or something like that. So this is a very effective way of making sure that the communication between two circuitries is happening properly and proper data is getting transmitted. So now let us see how to design a parity checker, because it sounds very interesting, right? It's a very what do you say, it's a very useful circuitry for us as engineers. So how do we design it? So let us have a problem where we have to design a product of sum circuit that will detect even parity for a 4-bit binary signal. So let us assume that A, B, C, and D are the inputs and P is the output or the parity bit. So if I want to write the truth table, I just write down the values of different combinations for A, B, C, D. Now parity, it'll be 0 if there are even number of ones in your input signal, right? If there are odd number of 1, then if I set the parity to 1, then the whole signal becomes even. So we have to take into account the parity bit as well to make sure that our signal is even. Like our signal or our whole binary digit has got even number of ones. So for the sake of parity generation, we keep ones in the output or in the P bit, where if the number of ones in A, B, C, D are odd. If the number of ones in A, B, C, D are even, then the parity bit is 0. So this is the logic behind even parity generator. So now if I see the K map for P, since I'm writing a product of sum like circuit, I'm designing a product of some circuit, or I'm asked to design a product of some circuit, I shall consider the zeros in my K map and simplify them. So wherever there was 0 in my truth table is the ones that I'm going to use to simplify my K map. So we can see that there's a checkerboard pattern of zeros and ones in the K map that after populating it. So checkerboard pattern usually refers to an exclusive OR function. Now, if you don't want to buy what I'm trying to say, go ahead and write the Boolean expression for all the cells that have zeros in them. So P is A plus B plus C plus D into A plus B plus C dash plus D dash into A plus B dash plus C plus D dash into A plus B dash plus C dash plus D into A dash plus B dash plus C plus D dash C plus D into A dash plus B dash plus C dash plus D dash into A dash plus B plus C plus D dash into A dash plus B plus C dash plus D. If you use your Boolean theorems and laws, you will ultimately find out that this simplifies to A exclusive OR of B, exclusive OR of C, exclusive OR of D, right? So if I want to realize this equation in a logic circuit, then I require three exclusive OR gates, right? Because we know that exclusive OR is a two input logic gate. So per OR gate, I can only use two inputs. So in the first logic gate, I give A and B as input, and the output is exclusive OR, and that is fed to the second logic gate. And the other input for the second logic gate is the variable C. Now these two are exclusive OR, so the output becomes A exclusive OR of A, B, and C, and that is fed to the third exclusive OR gate, and the other input for the third exclusive OR gate is my D. So ultimately, P is exclusive OR of A, B, C, and D. Now it is worth noting that odd parity generator is a complement of the even parity generator. So if you design an even parity generator and put a NOT gate in the output of the third exclusive OR gate, like just before taking P, if you just invert P, then you get the odd parity. I hope you had a fruitful session learning about parity generators with me. In your own time, I would highly encourage you to try out the odd parity generator and see whatever I've said matches with your results. Thank you very much for attending this session. I shall see you again soon. Bye.